projects. In this video, we are going to explain about the project title, an experimental analysis of deep neural network based classifiers for sentiment analysis task. Introduction. With the rise of the internet, social media and online platforms, there's been an explosion of user-generated content in the form of reviews, comments, tweets, and more. Sentiment analysis becomes crucial here to understand the opinions, emotions, and attitudes expressed in this vast amount of unstructured textual data. Traditional methods in sentiment analysis often required handcrafted features, which meant experts had to manually design features for the model to learn from. Deep learning models, especially neural networks, have revolutionized this field by automatically learning intricate patterns and features directly from the text, eliminating the need for manual feature engineering. Convolutional neural networks CNN and recurrent neural network RNN are powerful but have their limitations. RNN can struggle with retaining long-term dependencies due to issues like vanishing gradients or the difficulty of remembering information from the distant past. CNN, on the other hand, might not capture sequential information effectively. The proposed model combines different architectural components, transformers, bidirectional LSTM, BiLSTM, and convolutional neural network CNN. Transformers are excellent at capturing global dependencies in text. BiLSTM can understand sequential information bidirectionally, and CNN are good at capturing local patterns. Combining these aspects in one model creates a powerful system for sentiment analysis. This model claims high accuracy in sentiment analysis while having fewer trainable parameters compared to large pre-trained language models like BERT. This reduction in parameters potentially makes it more feasible for smaller companies or individuals with limited computational resources to utilize this model effectively without needing extensive computational power. Objective. The primary goal here is to experimentally explore the efficacy of deep neural network based classifiers in handling sentiment analysis tasks using textual data. This suggests an investigative approach to understand how these neural network models perform specifically in discerning sentiments from text. The project involves not only assessing already established models used for sentiment analysis, but also proposing novel models. These models are likely designed to enhance sentiment analysis accuracy, possibly by integrating different word embeddings to comprehend the nuance of sentiment expressed in text more effectively. The project focuses on combining two distinct deep neural network architectures, bidirectional long short-term memory BiLSTM and convolutional neural network CNN. By merging these architectures, the aim is to capitalize on their unique strengths. BiLSTM are adept at capturing sequential information bidirectionally, while CNN excel at recognizing local patterns within data. This amalgamation seeks to improve accuracy by leveraging the complementary capabilities of both architectures. The proposed models and the insights gathered from this project could be beneficial for other researchers in the field of sentiment analysis. By evaluating different word embeddings and developing new models, this research contributes to the understanding of which embeddings are more effective in sentiment analysis tasks. Furthermore, sharing the findings can guide future researchers in selecting appropriate word embeddings and architectures for their sentiment analysis models, potentially advancing the field. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of i5 and above, RAM of 8GB and above, hard disk of 25GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This module involves importing necessary libraries and packages in the chosen programming language. These packages typically include libraries for data manipulation like pandas, natural language processing like NLTK, visualization like matplotlib or seaborn, and machine learning such as scikit-learn or TensorFlow. Exploring the dataset SST2 dataset. This step involves understanding the structure and content of the SST2 dataset, which likely contains text data labeled with sentiment, positive or negative. This exploration includes examining the size of the dataset, understanding its columns or fields, and gaining insights into the distribution of sentiment label. Visualization. Visualization helps in gaining a better understanding of the dataset's characteristics. Visual representations like histograms, pie chart, or word clouds might be used to showcase the distribution of sentiment analysis, word frequency, or any other relevant patterns in the data. Data processing. This module involves several substeps to clean and pre-process the text data before feeding it into the sentiment analysis model. Removing the URL and other characters. Eliminating URLs and special characters that don't contribute to sentiment analysis. Remove punctuations. Stripping away punctuation marks like periods, commas that do not carry sentiment information. Remove stop words. Stop words are common words like and, the, is that often don't contribute much to sentiment and can be removed to focus on more meaningful words. Normalization the data. Normalizing text involves converting words to their base or root form, lemmatization, to reduce words to their canonical form, example running to run. Tokenize the words and lemmatize. Breaking text into individual words, tokenization, and then reducing those words to their base form, lemmatization, to handle variations of the same word. Vectorizer the text lexicon-based approach. Transforming the pre-processed text into numerical form using lexicon-based approaches like bag of words or TF-IDF, term frequency inverse document frequency. This step converts the text into a format understandable by machine learning models, assigning numerical values to words based on their importance in the document. Feature extraction, word to vector. This technique represents words as dense vectors, capturing semantic meanings by considering the context in which words appear. It converts words into numerical vectors, creating word embeddings. Word embeddings. Similar to word to vector, word embeddings represent words as dense vectors, often learned from large text corpora, to capture relationship between words based on their context. Feature selection involves choosing or extracting the most relevant features from the data. This step involves techniques like selecting the most important words or word embeddings based on their significance in predicting sentiment. Splitting the data to train and test. Dividing the dataset into training and testing sets. The training set is used to train the sentiment analysis model, while the testing set evaluates its performance on unseen data. Building the model, developing the sentiment analysis model architecture using deep neural network based classifiers. This step involves defining the structure of the model, specifying layers, activation functions, and other parameters. Training the model. This involves feeding the prepared data into the model to learn patterns and relationships between the input features and sentiment labels. The model's parameters are adjusted iteratively to minimize the prediction error. Flask framework with SQLite for sign-up and sign-in. Implementing a web framework like Flask along with SQLite database for user authentication, allowing users to sign up and sign in to the application. User gives input. Users provide input text for sentiment analysis through the application's interface. The given input is pre-processed for prediction. The user's input undergoes pre-processing steps to clean, tokenize, and convert it into a format suitable for predicting the model. Trained model is used for prediction. The pre-processed user input is fed into the trained sentiment analysis model to predict the sentiment, positive or negative. Along with that, we applied LDA model for topic modeling. Apart from sentiment analysis, the project also involves latent direct allocation (LDA) or topic modeling technique to identify topics present in the text data. Final outcome is displayed through front end. The final sentiment analysis prediction, possibly along with topic modeling results, is presented to the user through the front end of the application, providing an accessible interface to view the analysis outcomes. Algorithms used to implement this project, we have designed the following algorithms. The first algorithm is CNN plus BiLSTM. CNN, convolutional neural network, utilizes convolutional layers to extract local features or patterns from input text. BiLSTM, bidirectional long short-term memory, processes sequences bidirectionally, capturing context from both past and future. Combination of CNN plus BiLSTM. The CNN component first extracts local patterns or features from the text data. These extracted features are then fed into the BiLSTM, which captures the sequential context within these features. This combination aims to leverage CNN feature extraction ability and BiLSTM capacity to capture sequential relationships for sentiment analysis tasks. BiLSTM plus CNN plus BiLSTM. BiLSTM, efficient in capturing bidirectional context and sequential data. CNN extracts features from the input text. The combination of BiLSTM plus CNN plus BiLSTM begins with the BiLSTM layer to capture bidirectional context from the raw text, followed by a CNN layer to extract features based on this contextualized representation. Concludes with another BiLSTM layer to further process these extracted features, capturing deeper sequential relationships within the text data. CNN, convolutional neural network. CNN are neural networks primarily used for image recognition, but they are also effective for text analysis. They consist of convolutional layers that apply filters to identify local patterns in input text. In the context of text analysis, CNN can learn to identify important textual features or patterns within a sequence of words by applying convolutional filters, capturing aspects like n-grams or word sequences. Transformer CNN. Transformer utilizes self-attention mechanism to capture relationships between words in a sequence more effectively. CNN, proficient in local feature extraction. The combination of Transformer CNN integrates the self-attention mechanism of a transformer model with the feature extraction capabilities of a CNN. The CNN initially extracts local features from the text, followed by the transformer component processing these features to capture both local and long-range dependencies efficiently for sentiment analysis tasks. Transformer CNN plus BiLSTM. Transformer CNN, combination of transformer and CNN architectures. BiLSTM captures bidirectional sequential dependencies. Combination of transformer CNN plus BiLSTM utilizes a transformer CNN initially to process and represent the text comprehensively, capturing both local and long-range dependencies effectively. The output from the transformer CNN is then further refined by a BiLSTM layer, extracting nuanced sequential patterns and context within sentiment analysis task. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graph. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have the FN score, and on the y-axis, we have the algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contain algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flash framework will host the application locally at the default address, localhost, which is this, and port, which is this. Now copy this local link provided by the Flash framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first, so click on sign up button. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have created and then click on login. We have logged in successfully. So here we need to enter the message, and after entering the message we will predict the type of the message, whether it is positive or negative. So I'm entering the message. So here I have entered the message. Now click on predict button. So here this is the message which we have entered, and the label for the message is The text type is negative. The topic for the paragraph is most dependent upon these words. Now we will enter some more messages and check the text type. So I'm entering one more message here. So here I have entered this message. Now click on predict. This is the message which we have entered. The label for the message is the text type is negative. The topic for the paragraph is most dependent upon these words. Now we will enter some more messages and check the text type. So I'm entering one more message here. This is the message which we have entered. Now click on predict. The label for the message is the text type is positive. The topic for the paragraph is most dependent upon these words. So in this way, by entering the message, we can predict the text type, whether it is positive or negative. The conclusion of the project is, the project aimed to explore various deep neural network based models for sentiment analysis using textual data. This involved testing and evaluating different architectures to determine their effectiveness in analyzing sentiment from text. The proposed transformer bi-LSTM CNN model, which combines different word embeddings, demonstrated high performance on the SST2 dataset. This model likely showcased superior accuracy in identifying sentiment compared to other models experimented within the project. The inclusion of transformer encoder layers alongside CNN architecture showed a noticeable enhancement in accuracy compared to using CNN alone. This improvement suggests that leveraging the attention mechanism of transformers complemented the local pattern recognition abilities of CNN for sentiment analysis. The project compared the proposed model's performance with larger pre-trained language models such as BERT. Despite being a task-specific model, the proposed approach exhibited advantages in terms of computational efficiency and performance on datasets specifically tailored for sentiment analysis tasks. This indicates that while models like BERT are powerful, task-specific models can offer comparable performance with fewer computational resources. The findings from this project offer valuable insights for researchers in the field of sentiment analysis. Specifically, it provides guidance in selecting word embeddings and developing sentiment analysis models tailored to specific tasks. By showcasing the effectiveness of different architectures and embeddings, it aids researchers in making informed decisions for their own model development.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.